what we started 10 years ago with the idea, and the idea is our smart factory. In that day or in that time, we think about a smart factory, but what means smart? And the video is gives you a little bit the idea of, in a funny way, about what we want to achieve. So please. Oh, yeah, okay, perfect. Thank you.
Yeah? Tonight? Okay. Thank you.
On production?
Yes, I got a new job at.
Me too. Mine's running already.
Huh?
So that was the idea, but is this reality? And what we learned in the last years, it's not so easy to achieve this idea. So flirting at the next level, all the information's on your fingertip with an autonomous smart factory who control themselves and get time for the people back in a smart way to empower that. It's not so easy as we learned, and is that what we have to understand. So we started as a machine builder in the 50s. Okay, we built some machines, and what we do was to automate these machines. And what we saw in the presentations before, we connected the machines. And as we started to get an IoT understanding, we get an under picture of our products, because the machine produces a lot of data, and we collect the data with no idea what we can do with them. And we learned with the connected machines also how to use this data and how to predict some things. And it's clear what we want to achieve with this idea in behind because of the smart factory. And that is what we do, and we learned a lot of. So if you don't do connected the machines or collected the data from the shop floors, nothing will be happened. If you do that, you learned a lot, and we learned what could be achieved also for predictive maintenance and all this kind of stuff. And we struggled. Why? So we tried to collect all the data to a single platform, like the platform economy. We built up some startup with Axum, and we have the hope that we collected all this data to find out and to predictive and to maintenance and all this kind of stuff, what you can do with the data. You will see it at the Bosch side with the dashboards. And what we learned is the customer didn't want to share the data. Very not so easy to come in and to bring up this kind of service to the customer side. And that was the beginning of the ecosystems. So we tried to change the paradigm to use the machines at the customer side and to learn to control the machine with the data we get. And that was the start of the idea of the ecosystems, because that was the reason to get another point of view, to use the machines not as a machines, but to think about how can we use the machines on the shop floor with everything as a service. So we change our thinking about the production machines as we has, and we think about to achieve all as a service. And with this thinking model, you learned a lot of to get the data, because you need the data to provide a service. And that was the reason to change the architecture of the shop floor system. And As an example how we tried it, so we have a concrete use case for remote operations. So we started to connect to the machine, and we are able to jump to the machine from the distance and to remote the machines collected by the data and the cameras and all this kind of stuff what's inside the machine. And that was interesting because we learned a lot of not to operate the machine for maintenance, for example. So in the past, the customer have a problem, he called at our site, and we could help the customer in this connected machine world. And with that, in combination with AI, we have learned to use this data for remote operations, but not also for remote operations, because at the customer side there was another problem. Because, for example, the customer have an order to over the weekend, and he has no operator. And we have the idea to say, okay, that's very interesting, so we can offer a new service based on the data, based on the connections, based on the ecosystem, to help the customer, combined with the AI, to operate as a service. It's new. And that was very interesting, and that's what we learned. And here in this small video, you see how it works. So we stay here with the operational center, and today there's a human in the loop because you have to control all that kind of AI algorithm who scaled it up. And at the end, the human in the loop make the decisions to produce or not to produce. So at the moment we need that, but in the future maybe we have better AI technologies to control it. We research on this topic to make releases with the AI. It's new, so but we are very on a good way. So we will see that will happen in the future. And with this, combined with the AI technologies, we can scale up a lot of shop floor machines to be self-empowered and self-regulated. And that was very interesting. So there are new business and new services we can now offer for our customer side. The last point is an example. What we can do is with AI, so we can control the machine parameters. So here you see we can detect it, the edge, the cutting edge, and the AI in the machine is a real AI. Trained and learned to control the machine parameters for the perfect cut. Doesn't matter which material you put in the machine. And that was very dramatic for the machine operator, because in the past the machine operator has a deep knowledge to control the machine parameters to get the best cut. In the future we have AI in this machine, so he's the cutting expert in the machine, and the operator it doesn't need anymore in the future. But we have to think about how to scale up, because this is one machine with one AI, but there's a lot of more machines, and we have to change the data to train the system, and that what industrial AI means. It's if you try to get this kind of models on the internet, you didn't find any data about to train this kind of models. It's a special industrial thing, and the decisions will very clear on the industrial way. So at the end, you can put on some predictional AI inside the components of the machine. So we are able to predict the failure of components inside the machine, and it's dramatic to the service, because if the machine has a failure, the customer calls to the service, said, oh, I have a problem, the machine is standing, help me. And that on the other side, at the TRUMPF side, we have a bit of problem, because we have a priority one. We have to go very fast to the customer with the right spare parts, and then we have a lot of pressure inside. And with this kind of predictional components, the components will be informed, oh, in 3 or 4 days I have a failure, and we can manage all this kind in the back office and we have then not a priority 1 failure, but a priority 3, and we have more time to organize all this kind of stuff we have to do to make the repair on the machine. Another thing is a technical guide, so we are able to put and to collect all this knowledge, what we learned. And that is the interesting thing, what we learned together, also on the shop floor side with our customer, to fulfill and to get a guidance, a technical guidance who helps the customer very fast. And that is knowledge. Knowledge at its best, not as a handbook, but in future, maybe on AI, because the customer can ask the AI and get precise answers. So that is that from our perspective, what we learned in the last years, and we want to share that because we are it's clear to make more innovations in a collaboration way, and we learn together. We learn together how to use that, how to form that, how to transform it, and how to build up new business models. And the next thing is in the interconnect data supply chains with digital twins. The next step will be combined AI, and my predecessor talked about the autonomous factories will be there with, and it will be started with the autonomous machines, and we get the freedom to operate back to the customer. That's the core idea. Thank you, and I will hand over now to Sebastian.
Okay, yes, thank you very much. Maybe before starting, before we had the presentation from Dr. Nagano regarding what's the difference between Industry 4.0 and Manufacturing X, and maybe I don't have to have a slide right here, but maybe a short comment. So Industry 4.0 for us, it was like one machine, a lot of sensors inside and visualizing the sensors or the status of the sensors on an app, but focus on one machine. Now with Manufacturing X, and that was also in the slide a little bit, the connection between the machines, between then the operator of the machine, us as machine tool builder, and maybe the suppliers of the components of our machines. And so the interaction between all the different machines and exchanging the data between the machines. So that's more or less the step between Industry 4.0 and Manufacturing X. Now I want to show, let's say, some use cases or a focus on Aerospace X. I think aerospace is a very important market in India, growing quite a lot. That's why I want to show there some topics we are doing in Aerospace X. What is written here, I don't want to show that in detail, but 3 cases, and the main result of these 3 incidents is more or less there is no problem regarding the material, the problem is regarding the machining process. And of course, it's in aerospace, it's always like this. If you have a problem in any kind of component or any incident, you need to check if there is any incident further on, or if there are maybe other components could be influenced by that. That's why we started the project regarding Aerospace X. So it started quite similar to Factory X. And there are 4 use cases: capacity management. You know, Airbus, for example, has a lot of problem regarding the delivery of the machines, the time. And then circular economy, CO2 footprint, of course, that's everywhere a topic, and end-to-end quality management. So exactly that topic which I showed on the slide before. For supply chains, cabin, then hull, and we are now in the supply chain of engine, because in engine there are a lot of milling parts inside what we can focus on. Now a short overview about, let's say, the complete supply chain. So on top you have the aircraft manufacturer like Airbus, then below you have the system integrators for the landing gear, engine and cabin and so on, then the equipment integrators for the fuselage sections and the engine modules, part manufacturers, and also the raw material manufacturers. Then there was a survey question was, what are the biggest challenges in end-to-end quality management? And there are 3 cases. First is inspection of non-conforming components, then root cause analysis and problem solving. Actually, that's the topic what I mentioned before. And then certificate of conformity. So just to show which of the topics are important for all these kind of companies. And then just to give you an idea how complex is the topic of traceability in aerospace. So a passenger jet consists more or less out of 3 million parts, so quite a huge number of parts. Then there are several thousand suppliers in that. Actually, here I think Airbus, for example, works together with 3,000 suppliers directly, but of course there's then also a network of around 18,000 suppliers for the complete supply chain. So that's more or less the overview, just to see how complex that is. And if there is any incident, then you need to get in contact with all of these suppliers, or at least some of these suppliers, and that's quite a huge number. What we want to show here is one example, a low pressure turbine disc. Actually, it's a generic part of it, so it's not reality, but it could be in any kind of turbine used. These are the operational data. Then I also don't want to show it or discuss it in detail, but that's more or less the core idea behind that. If you look to the complete process of manufacturing these parts, then you have the forging supplier where you're coming from the raw material. Then then you have the supplier regarding mechanical processing. Then you have maybe some special processes like shock blasting or some thermal coatings or something like this. And you have then at the end the assembly, so the module level and the engine level, just to show you the different levels and also the different steps, the different machining steps and the different suppliers, which are only let's say in the complete process of this small part, just to show how complex the process is. That's now more or less here then the actual process. Also you have the different let's say stakeholders, and you have the different processes. And at the moment the situation is like this, that you have more or less documents, manual documents, and PDFs, papers, and so on, and very, let's say, a very fragmented and heterogeneous documentation. So in any kind of incident, you would need to check any document and ask every of these companies if they're to see how the documents or what's inside the documents. What we are doing now in Aerospace X, all of that data exchange is done by asset administration shell to exchange the data in a systematic way, and also if there's any problem at the end to see how you can get the data automatically by asset administration shell. So that's more or less the way how we do that, describing all the parameters of the process with asset administration shell, and to bundle all the data in a digital twin. Here now, that's now the result more or less. You get at the end, you get a digital twin of the process, so of the part of the workpiece, but also of the process, of the different steps of the process. And then you can also analyze later on if there are any problems in the process. You can analyze where are the problems, and you can also then, if you have the problem, you can analyze that much easier in other parts which are manufactured in the same way, and check if there are maybe some problems which could be where you see which could be also affected. So what Thomas Hahn also mentioned, if you have then if you need to get back some of the components, you can much easier detect which of the components are affected. That's now the process, the idea, what is coming out at the end. So handling with a digital twin based on asset administration shell to digitally analyze all of these parameters. That's it, more or less. Thank you very much. And